Hey there, science fans! Today we're diving into the fascinating world of chemistry. Have you ever wondered what makes up everything around us? Well, it all boils down to pure substances and mixtures. Pure substances are like the superheroes of the chemistry world. They're made up of only one type of element or compound. Think of pure gold, a shiny element, or pure water, a compound made of hydrogen and oxygen. These substances are the real deal, with consistent properties throughout, but hold on. Not everything is pure. In fact, most of the stuff we encounter daily is a mixture, a combination of two or more pure substances. Mixtures are like the sidekicks, always there to mix things up. Now, imagine mixing sugar into your lemonade. That's a mixture. You're combining two different substances. Mixtures can be found everywhere, from the air we breathe, a mixture of gases, to the soil beneath our feet, a mixture of minerals and organic matter. So there you have it. Pure substances are the building blocks, while mixtures are the exciting combinations that make our world so diverse. Stay tuned as we explore the different types of mixtures and how we can separate them. Remember those pure substances we talked about? Well, in the real world, it's pretty rare to find them in their perfectly pure form. Most substances have a little something extra mixed in. We call these impurities. Impurities are like those uninvited guests that show up to a party. They tag along with our pure substances, sometimes in tiny amounts, sometimes in larger quantities. Think about a pinch of salt accidentally mixed into a bowl of sugar. The salt is an impurity in our otherwise pure sugar. Now, impurities aren't always a bad thing. Sometimes they can be intentionally added to change a substance's properties. For example, adding a bit of carbon to iron creates steel, which is much stronger than pure iron. But sometimes impurities can be undesirable, like when harmful bacteria contaminate our drinking water. Understanding impurities is crucial in chemistry because they can affect how a substance behaves. Scientists spend a lot of time and effort trying to remove impurities to obtain substances as pure as possible for their experiments and applications. So, the next time you hear the word impurity, remember it's not always a villain. Sometimes it's just a matter of perspective. Now that we've met the players' pure substances and those sneaky impurities, let's dive deeper into the world of mixtures. It turns out not all mixtures are created equal. We can divide them into two main categories: homogeneous and heterogeneous mixtures. Homogeneous mixtures are like the best-dressed groups at a party. Everything blends seamlessly. In a homogeneous mixture, the different components are evenly distributed throughout, making it look like one uniform substance. Think of salt water. You can't see the individual salt crystals because they're dissolved and evenly spread out in the water. Heterogeneous mixtures, on the other hand, are more like a lively dance floor. You can easily spot the different parts. In this type of mixture, the components don't mix evenly, so you can see distinct regions or phases. Imagine a bowl of cereal with milk. You can clearly see the cereal pieces separate from the milk. Understanding the difference between homogeneous and heterogeneous mixtures is important because it helps us choose the right techniques to separate them if needed. And trust me, separating mixtures is a big part of chemistry. So, next time you're stirring your morning coffee or mixing up a batch of cookies, take a moment to appreciate the science behind the mix. Now that we've explored the fascinating world of mixtures, it's time to tackle a common challenge: separating them. Just like sorting laundry or organizing your sock drawer, separating mixtures is all about finding the right technique for the job. Luckily, chemists have developed a whole arsenal of separation techniques, each tailored to specific types of mixtures. One of the most common techniques is filtration, which is perfect for separating solids from liquids. Think of making coffee. The filter paper traps the coffee grounds, solid, while allowing the brewed coffee, liquid, to pass through. Another essential separation technique is distillation, which is ideal for separating liquids with different boiling points. Imagine distilling salt water to obtain pure water. We heat the salt water, causing the water to evaporate and leave the salt behind. The water vapor is then collected and cooled, condensing back into pure liquid water. And then there's chromatography, a versatile technique used to separate mixtures based on their different affinities for a stationary and a mobile phase. Think of separating the colors in a black marker using paper chromatography. The ink travels up the paper at different rates, revealing the individual colors. These are just a few examples of the many separation techniques used in chemistry. Each technique relies on the unique properties of the substances being separated, allowing us to isolate and purify the components we need. Section 5. Everyday Chemistry Separation in Action. Separation techniques might sound like something out of a science lab, but believe it or not, we encounter them all the time in our daily lives. From the kitchen to the environment, these techniques play a crucial role in making our world tick. Let's start with something we all know and love: cooking. Straining pasta is a perfect example of filtration in action. The colander acts as our filter, separating the cooked pasta, which is a solid, from the hot water, which is a liquid. Now think about that refreshing glass of orange juice you enjoy in the morning. The juice is often made from concentrate, which is produced by evaporating water from fresh squeezed orange juice. This process, you guessed it, is a form of distillation. And remember those colorful candies we saw earlier? They get their vibrant hues from food coloring, which is often a mixture of different dyes. Manufacturers use chromatography to separate and purify these dyes, ensuring that each candy has its signature color. These are just a few examples of how separation techniques sneak their way into our everyday lives. So, the next time you're separating laundry, brewing coffee, or even just admiring a rainbow, take a moment to appreciate the chemistry at play. Section 6. Solid ground. Separating solids from liquids. We've already dipped our toes into the world of separation techniques, but let's focus on a specific challenge: separating solids from liquids. This is a task we encounter frequently, whether we're making tea, cleaning up a spill, or even treating wastewater. One of the simplest and most effective methods for separating solids from liquids is decantation. This technique relies on gravity to do the heavy lifting. Imagine you have a mixture of sand and water in a beaker. If you let the mixture settle, the denser sand particles will sink to the bottom while the water remains on top. We can then carefully pour off the water, leaving the sand behind. Another common method is centrifugation, which speeds up the separation process using centrifugal force. Think of a salad spinner. As the spinner rotates, the water droplets are flung outward, separating from the lettuce leaves. Centrifuges work in a similar way, spinning mixtures at high speeds to separate components based on their densities. And of course, we can't forget about filtration, our trusty technique for separating solids from liquids. We've already seen how it works with coffee, but filtration is also used in a wide range of applications, from purifying drinking water to removing impurities during chemical synthesis. So whether you're dealing with a sandy mess, a cloudy liquid, or just want to enjoy a clear cup of tea, remember that there's a separation technique out there to help you achieve solid ground. Section 7. Filtering out the fun. How filtration works. Filtration is like the superhero of separation techniques, swooping in to save the day when we need to separate solids from liquids. But how does this seemingly magical process actually work? The secret lies in the filter, a material with tiny pores or holes that act like a selective barrier. When we pass a mixture through a filter, the liquid components, being small enough, can pass through the pores, while the larger solid particles get trapped. Think of it like a sieve separating flour from lumps. The fine flour particles pass through the mesh, while the larger lumps are left behind. Similarly, in filtration, the filter paper or membrane acts as our sieve, trapping the solid particles while allowing the liquid to flow through. The type of filter used depends on the size of the particles we want to separate. For coarse separations, like removing sand from water, we can use simple filter paper. But for finer separations, like removing bacteria from drinking water, we need specialized membranes with incredibly small pores. Filtration is a versatile and essential technique used in countless applications, from brewing our morning coffee to ensuring the purity of our medicines. So, the next time you reach for a filter, take a moment to appreciate the science behind this seemingly simple yet powerful separation method. Section 8. Distillation decoded from liquid to vapor and back again. Distillation might sound like a fancy word, but it's actually a pretty straightforward process that takes advantage of a simple principle. Different liquids boil at different temperatures. By heating a mixture of liquids, we can selectively boil and collect the component with the lower boiling point, leaving the other components behind. Imagine you have a mixture of water and alcohol. Water boils at 100 degrees Celsius, while alcohol boils at a lower temperature of 78 degrees Celsius. If we heat this mixture, the alcohol will boil first, turning into vapor. We can then collect this vapor and cool it down, causing it to condense back into liquid alcohol, now separated from the water. This process of heating, vaporizing, cooling, and condensing is the heart of distillation. We use a special apparatus called a still, which typically consists of a heating flask, a condenser, and a collection flask. The mixture is heated in the heating flask. The vapor rises and travels through the condenser, where it cools and condenses back into liquid, which is then collected in the collection flask. Distillation is used in a wide range of applications, from producing alcoholic beverages to refining crude oil into gasoline and other fuels. It's a powerful technique that allows us to separate and purify liquids based on their boiling points, playing a crucial role in various industries and scientific fields. In Section 9, Chromatography chronicles separating colors and more. Chromatography might sound like a mouthful, but it's simply a technique that separates mixtures by exploiting their different affinities for a stationary phase and a mobile phase. Think of it like a race where different runners have different speeds. In chromatography, the runners are the components of our mixture, and the racetrack is made up of the stationary and mobile phases. The stationary phase is like the track surface, usually a solid or a liquid coated on a solid support. The mobile phase is like the wind, usually a liquid or a gas, that carries the components of the mixture along the stationary phase. As the mobile phase flows through the stationary phase, the different components of the mixture will interact with the two phases to different extents. Components that have a strong affinity for the stationary phase will move slowly, while components that have a strong affinity for the mobile phase will move quickly. This difference in speed causes the components to separate, allowing us to identify and even collect them individually. One of the most common types of chromatography is paper chromatography, often used to separate inks and dyes. In this case, the paper acts as the stationary phase, and a solvent, like water or alcohol, acts as the mobile phase. As the solvent travels up the paper, it carries the ink components along, separating them based on their different affinities for the paper and the solvent. Chromatography is a powerful and versatile technique used in a wide range of applications, from analyzing complex mixtures in forensic science to purifying proteins and other biomolecules in biotechnology. It's a testament to the ingenuity of chemists and their ability to exploit subtle differences in molecular properties to separate and analyze the world around us.